Alright, welcome back everyone. Moving on to the skeletal system. Not particularly concerned about which bone is which at this point, but more looking at the bone tissue, how it develops, how it maintains itself, other effects it has on the body. So our 5 functions, key functions of the skeletal system, it's there to support bones hard and rigid. We also have cartilage, flexible yet strong, ligaments connecting bone to bone, tendons connecting muscles to bones. Remember, bone is all connective tissue, and its primary purpose is there to support our body. It protects. We have the skull around our brain, ribs, the sternum, and vertebrae protect our thoracic cavity organs. Allows us to move by muscles attached to bones via tendons. We have ligaments in between bones to allow movement but prevent excessive movement. It's also used as a storage medium for our calcium and phosphorus ions. They're stored and then released as needed. Fat stored in the marrow cavities. Blood cell production, so all of our blood cells are created in that bone marrow. We have our five classifications. So let me turn my flat bones, such as the sternum, such as parts of the skull. It is there to, I'll just go in order. So we have long bones, femur, all of our appendicular skeleton, all the long bones in the appendicular skeleton, there to provide support and facilitate movement. Short bones, we say short, think cuboidal, so they are just typically about as wide as they are long. They're there, such as the carpals and tarsals, mainly involved in providing stability and limited motion. Those bones don't have much flexion between them. A lot of them are fused together. Flat bones, thin flattened bones like the ribs and the scapula, serving as protective shields for vital organs. Irregular bones, think of the vertebrae, think of a lot of areas of the pelvis. Complex shaped bones, contributing to structural support and protection in various body regions, also allowing a lot of different muscle attachments, specifically with our spine. And sesamoid bones, small rounded bones like the patella. The patella is the only example probably that you'll ever need to know. There can be other sesamoid bones, specifically within around our phalanges. But if this question ever comes up, probably in college too, it's usually about the kneecap, the patella. The skeletal system generally made up of 206 bones, so there will be some variance with people. Axial skeleton, so thinking about our core, around 80 bones, and appendicular skeleton, 126. Like I said, next week we'll get more into what bone is where. You should at this point be able to differentiate axial in our core and appendicular in our extremities. But beyond that, we'll get more specific next week. So our bone structure, so our diaphysis, the shaft of the bone, is primarily made of cortical bone. You've also heard of that referred to as compact bone. It's surrounded by the periosteum, so it's a membrane-provided entry and exit points for the, what did I write, BV? Blood vessels and nerves. That's a stupid abbreviation. Blood vessels and nerves. It's also, it's where the blood supply around the bone is maintained. We have all our nerves there. All of our osteoclasts and osteoblasts are also found within that periosteum, working on the cortical bone. At the center, we have the medullary cavity, filled with yellow bone marrow, which is just our adipose tissue, it's just fat storage, aligned with the endosteum on the inside. We do have these nutrient arteries we have nutrient veins. I don't know why they're never shown these pictures. Nutrient arteries, nutrient veins coming into this marrow, as well as into the red bone marrow up here. So the epiphysis, the ends of the long bones, it's made of that trabecular bone, also known as the spongy bone. Contains red bone marrow, site of hematopoiesis, so that's our generation of blood cells, both white and red. It's covered with articular cartilage, so think of the hyaline cartilage. This is that, we need a drumstick, that really white, smooth cartilage on the end of it. That's there. It's there to reduce friction, and as well as wear and tear on the bone. When people have bad arthritis, that wear and tear arthritis, that wears down they start getting right onto the, we have a little bit of cortical bone up there, but into the spongy bone right below that. That's where we start getting issues. Contains the epiphyseal line / plate. You see we have one on top, one on bottom. This is our growth plate. Also made of hyaline cartilage. Eventually, when you're done growing, it will ossify into bone and no longer allow you to grow anymore. Just another view. We see our yellow bone marrow. I'm hoping to do a lab this week where I'm going to bring a saw and we're going to cut some fresh bones down the middle, remove some of that yellow bone marrow. These nutrient vessels are very large, and we can actually be able to pull them out and see them. We'll be able to peel off that periosteum along the outside of the bones. So I'm hoping. If not, I have a preserved version of this with a bone, but that's not as fun. I don't think there's anything I didn't cover in here. Those Sharpie's fibers, that's kind of that's that CT holding that periosteum to the bone. When we actually, hopefully we will have these bones. We'll try pulling that off. It's very tough to get off. So our bone marrow, we have red and yellow. You see here with the age progression, most of these long bones are filled with the red bone marrow at the beginning. Babies have tons of fat storage throughout their body. You see they get those 4 elbows. They don't necessarily need that yellow bone marrow in their bones yet. So they do need to create blood cells. So most of the bone is dedicated to red bone marrow at the beginning. As the child ages, we get more and more yellow bone marrow. I don't know how accurate this is. We don't have any spongy bone down here. But it does move from primarily red to primarily yellow as we age. That red bone marrow is found in that trabecular, remember, spongy bone. Blood cell formation, that hematopoiesis. Definitely going to ask you to define that on the test. Yellow bone marrow, it's only in that medullary cavity and functions in fat storage. So our bone tissue, I've already brought up cortical and trabecular. We'll differentiate them a little more. So cortical bone, aka our compact bone, it provides the structural support and protection. It's covered by that periosteum connective tissue. Composed of osteons. So the osteons, actually I have another slide. I won't get too specific. Cylindrical structures made up of concentric layers of bones matrix called lamellae. So we see that here. There's osteon in the middle. Undergoes remodeling throughout life. So it undergoes a lot of remodeling throughout puberty when we're actually growing in childhood. But we do continue bone remodeling throughout life. Depending on the forces we put on that bone. Our trabecular bone, it's aka spongy bone, aka cancellous bone, provides flexibility and shock absorption. That's not its main function, but it is there. It's highly vascularized. It's full of that red bone marrow, so obviously we have a lot of blood supply going through that. That creates our blood cells. Porous nature provides highest surface area to volume ratio versus cortical bone to facilitate exchange of nutrients and waste products. So remember, cortical bone, that medullary cavity, all we're doing is storing yellow bone marrow. Here, we're actually creating products. We're creating all the red blood cells, all the white blood cells, all the platelets. So we need a much more efficient exchange of nutrients. Did I write that multiple times? No, but we talked about it. So full of red bone marrow. 2 types of tissue within our bones. So we have organic tissue, which makes up 35% of the mass. It's made of our bone cells, so the osteocytes we see in the middle there, in those lamellae and those concentric rings. Osteoblasts here, remember, building up, and osteoclasts, breaking down in our bone remodeling. So in our organic matrix, aka the osteoid, right here. No, I'm sorry, right here, where these osteoblasts are putting down. So osteoclasts break down, osteoclasts build up, they secrete that osteoid, comprised primarily of collagen fibers. It serves as the framework for mineral deposition. So we create this framework of organic matrix, and in the next slide we'll see that the inorganic elements come and fill that in. Provides bone with tensile strength and resilience. So the inorganic matrix, which makes up most of the mass, mostly inorganic salt compounds, and is primarily calcium in the form of calcium carbonate and phosphorus in the form of hydroxylapatite. I think I'm pronouncing that right. So I know this looks a little different than what we were looking at with our valence electrons. I didn't know if I want to talk more about this, but I will. So remember, everyone wants its octet. So calcium has 2 on its what we call the valence shell. This might be new. So calcium obviously doesn't just have 2 electrons. Its atomic number is 20, so it's going to have 20 protons, and to maintain a neutral charge, it's going to have 20 electrons. It still wants to get an octet on its outer shell. It still wants its 8 electrons, and we see calcium's all the way on the left side of the periodic table in the second column, so it only has 2 electrons in its valence shell. It knows that if it gives those up, it's going to have a positive or negative charge. It's going to have a positive charge, 2 extra protons or 2 more protons than electrons, so it's going to have a 2+ charge as soon as this oxygen, which has 1, 2, 3, 4, 5, 6 valence electrons, it wants to steal these 2 to get its octet. It has its octet. It has its octet. We're great. The bond between them, they're not sharing electrons at this point. The oxygen has just stolen both of those. And in the case of the calcium carbonate, it taken 1 from each oxygen. So each oxygen has a partial negative charge, and the calcium has 2+. Now it's going to maintain this positioning. We still see we have CaCO3, so there's our CaCO123. There's no covalent bond between them, so this is just an ionic bond where we have this strong positive charge connected to this stronger negative charge. And we see the same thing in the hydroxyl apatite. So here, each oxygen has stripped 1 electron from this calcium. It still has an ionic bond to both of these. It's still going to maintain that position, even though they're not sharing electrons. Same thing with this calcium in the middle. So both of these calcium and phosphorus, they work together to form the inorganic matrix, and its function is to give strength to the bone. It's also storing calcium in our body, which we'll talk about in a second here. So the types of growth of our bones. So we have the longitudinal growth, whereas the bone's growing vertical along the epiphyseal plates, the growth plates, until those plates ossify. And then we have appositional growth, so the bone growth in diameter throughout life. That can be increasing or decreasing. This process is known as bone remodeling, which we talked about in human body systems. These 2 types work together to make the bones long enough and strong enough. So bringing this picture up, and let me get my pen out. I think it's on. Turn on the pen. Okay. All right, so our growth plate coming across right here. And we can see at our starting position, this bone wraps all the way around here. But what's going on right here, we see over here on this side. So at the very top, this resting zone. Oh, right up there. And on the other side here, we can see it's called the reserve zone. This is our matrix production. This is expanding that cartilage, right? Right below that, the proliferation zone from here to here. We have our chondrocytes, and they're undergoing mitosis. So also proliferation zone, proliferative zone. These cells are rapidly dividing in order to push that cartilage up. As we go down, the hypertrophic zone, or hypertrophy zone, or maturation zone, these cells are getting bigger. They're maturing into full cells right before they die. So we have this calcified matrix and cell death. This is when those inorganic compounds come in and ossify the now dead cartilage cells, expanding this ossification zone where our bone is actually growing up. So that's happening right down here. It's pushing up here. We're creating new cartilage this way, and the bone grows we can see, we'll do the opposite on the other side. Not only is the bone growing vertically, we also have to have the remodeling here, because same as this side, it was here, it was here. This is moving in. This obviously is moving out. So that is when we get our appositional growth. So just remember, just rapidly dividing cells, maturing, getting bigger, dying, and then getting ossified, getting calcified with those inorganic elements like calcium and phosphorus. And it's the same thing on the appositional growth, more specific. I mean, we saw it there with the bone remodeling over here. But specifically, this can be a result of changes in electrolyte balances in the body, whether the body says we need this calcium more for something else, we're going to strip it off the bones. These bones are going to show appositional decay. What's the opposite of growth? They're going to shrink. But normally, we're looking at ages here. So infant, obviously, we're going to have small bones. It's going to move out. And so we have that growth on the outside. This bone, this layer of the cortical bone on the inside is going to get resorbed by osteoclasts. So remember, osteoclasts break down, and then this outside edge through the periosteum, those osteoblasts are going to be building up more layers of cortical bone on the outside. So it really moves from inside to outside. It's not just, obviously we have more material here than we do here, so we're getting in more material, but remember, it's coming from the inside, moving outside, as well as from other sources. We're getting that additional bone tissue. So the regulation of bone growth, it is dynamic and active tissue. So that means its composition, its size, its shape is constantly changing and remodeling according to the activities we do. So the main factor is going to be calcium levels in our blood. Calcium's important for bones, but it's much more important for the nervous and muscular system to work correctly. Our body, bones are definitely the secondary, I don't know what the word I'm looking for is, not the priority. That priority is making sure our nervous function is functioning properly. We're able to transmit nerve impulses, making sure our muscular system is able to work correctly, to move us around, to digest, to do everything we need to do to beat our hearts. So if we are in hypocalcemia, our body's going to take that calcium from the bone. Those osteoclasts are going to break it down, and we're going to take it elsewhere. This picture over here, I was going to talk about how vitamin D is regulating, but it just got too complicated. I'm going to skip over that. So hormonal feedback to maintain the optimal ionic calcium levels in our blood. Like I said, this is our top priority. So a main factor that affects what our bone tissue does is our blood calcium levels. Optimal level is going to be that 9 to 11 milligrams per 100 milliliters blood. We don't need to remember that, but just know we have an optimal level. Calcium ions, like I said, calcium ions are very important for muscular nervous function, and our body cares more about that than our bones. So what we see is a feedback loop. Our calcium homeostasis, right around that 9 to 11 milligrams per 100 milliliters. If it gets too high, we have an imbalance this way. Our thyroid gland is going to recognize that and release calcitonin. And remember, that's hypercalcemia. So our body's going to release calcitonin. That calcitonin is going to stimulate calcium salt deposit, taking it from the blood, putting it into bone. Our bone mass is going to increase. If we imbalance the other way, we have falling Ca2 plus levels. We have hypocalcemia. It is going to promote reabsorption. So reabsorbing it from the bone and back into our blood supply. And that's coming from the parathyroid glands releasing parathyroid hormone. Osteoclasts, remember, break down bone, degrade bone matrix, and release calcium into the blood. And hopefully we get our level right there. Beyond the hormonal feedback, we also have mechanical stress. So the forces we put on our bones is going to change how our bones are modeled. Is that the right word? Maybe not. Keep bones strong is a secondary purpose. Wolff Law states that bones will grow according to the stresses placed on them. Activities that compress bones and pull on muscles, which pull on bones, can make bones stronger. So if someone's lifting heavy weights, their bones are actually going to get bigger and stronger. You could also think of a morbidly obese individual is more likely to ambulate with wider steps. So they're taking steps with a wider stance. That's going to put different forces on different parts of this bone, and we are going to actually change how that femur is, where the strong point is, depending where that where those points of stress we're putting on the bone are. Change to its shape. And together, remember, the hormones are determining when the remodeling will occur, and the mechanical stress determine where the modeling will occur. So both these processes work together to maintain our bone remodeling process throughout our lives. Bone development. So this is actually creating bones. Most bones are created through osteogenesis, ossification, through the endochondral route. So bone replaces cartilage. If we had this intramembranous route where bone develops directly from the mesenchyme, think of fetuses, or fibrous CT. So most of the time, this is well, I'll talk about this in a second. We also have calcification. Osteogenesis, ossification is a form of calcification. Usually when we use the word calcification, though, we're talking about the deposition of calcium salts on body tissue where we don't necessarily want it. So we have soft tissue calcification in the hand and wrist on this slide. We'll talk more about that in a second as well. But remember, this is a form of calcification, but this is basically the right way. And when we talk about calcification specifically, we're usually talking about bad things. So endochondral ossification, remember, this is where most of it happens, or most of the process is this way. So we have cartilage. Bone forms around the diaphysis of the hyaline cartilage model. So in fetushood, in pre-infancy, we form these cartilage bone shapes. We start building up. We start ossifying that cartilage, creates bone, creates all the structure we want. And that continues after birth. So at birth, I don't know what percentage it is of the newborn's tissues are still cartilage versus how much will develop into bone. I'm not sure. But it is still ongoing after birth. The intramembranous ossification. Remember, this is the other way it can happen, but it usually doesn't. This is mainly for the skull. So we have mesenchymal cells, embryonic connective tissue, which differentiates into cartilage, which is then replaced by bone. Wait, I'm sorry. In other areas. Okay, so this is not that. This is not mesenchymal differentiate cartilage replaced by bone. This is mesenchymal going directly and getting directly ossified. I don't necessarily care too much about you understanding that process, but just remember, intramembranous, we're going straight from the mesenchymal cells, those embryonic connective tissue, straight into bone, bypassing that cartilage stage. And then finally, our calcification of soft tissue. So the process by which calcium salts are deposited into soft tissues, resulting in hardening. Like I said, it can occur in the normal methods or through this abnormal. It can be metastatic calcification, which is normal tissue is for some reason calcified, or damaged dystrophic calcification tissues. Metastatic calcification results from hypercalcemia. So when it's going into normal tissue, it's because we have such a huge supply of calcium in our blood. Our body just says, get rid of it wherever you can. It's going to go into normal tissue and harden it. Can lead to formation of renal calculi, so kidney stones, gallstones, atherosclerosis. I should have put a slide of that too. So that, if you know what that is, great. It's our hardening of our arteries and other conditions. You see that? That's probably, I don't think that's coming out normally. That's probably a surgery, right? So right there at the start of the ureter coming out of the kidney. The small one, maybe they could pass. And last but not least, both of you are in patho, except for Ray. I'm gonna kind of test you on these fractures again. Nothing too difficult, just as a refresher. I'm not even gonna make slides. So our transverse fracture going straight across, our open or compound coming out from the skin. Our skin's broken. Oblique at an angle, at a diagonal angle, and then this is oblique non-displaced. We have oblique displaced where the bones are no longer lining up. We're gonna have to go in and actually do surgery. Comminuted multiple fractures. Segmental is also multiple fractures, but that interior piece is completely intact. An avulsion, a piece of the bone has sheared off, and usually that's going to be at a tendon attachment where that muscle's pulling harder than the bone can withstand. Remember, these two are pediatric suspect, usually, maybe it's not usually, but you're definitely thinking child abuse with spiral fracture and green stick. Green stick, remember, we still have that high degree of, we don't have full ossification of that cartilage tissue. So that bone can be much more flexible. It can actually split without completely fracturing. And then spiral is that, we call it a nanny fracture or nursemaid's fracture, where it's grabbing the arm and twisting as you're going, or the leg in this case, but it's a twisting motion, creating a kind of a rotated oblique fracture. I think that's the last one. Yeah, that's it. See y'all later.